Alright, now we're going to have a look at some applications of derivatives with exponential functions. And in this example, we have that the mass m grams of a radioactive substance is initially 20 grams. After 30 years, the mass is 19.1 grams. The mass in any year is given by m of t is equal to m0 multiplied by e to the negative kt, where m0 is a constant and t is the time in years. Now the first thing they want us to do is to calculate the value of the parameters m0 and k, and then hence calculate the amount of the substance remaining after a further 30 years. Alright, let's first define our variables, because in these sort of questions that's what we're expected to do. So we're going to let m of t be the mass at any time t, and remember that whenever we're defining, we're talking about the variables as well, so in grams, and we're going to let t be the time in years. Alright, now they've told us that m of t is equal to m0 e to the negative kt, and we need to look at the information that's being given to us in order to find out the values. So they say the mass is initially 20 grams, so that means when time is t is 0, so when t equals 0, m of 0 then has to be equal to 20. So we can use that information to say, well, that means that 20 is m0 e to the minus k times 0, and that becomes e to the 0, and anything to the power of 0 in the whole wide world is equal to 1. So therefore we know that m0 is 20 grams. We can use that as well as the fact that we know that after 30 years the mass is 19.1 grams. So we know that when t equals 30, we know that m of 30 is 19.1, and we can substitute our m0 equal to 20. So we have that 19.1 has to equal to 20 times e to the negative k multiplied by 30. And I can then divide both sides by 20, so I get 0.955 is e to the minus 30k. Now we're wanting to solve for k, and in order to solve for the exponent, we need to log both sides. So I'm going to take the natural log, 0.955 e to the negative 30k, and then using my log laws, I can take the negative 30k down. So I have ln 0.955 is negative 30k ln e, and obviously ln e is equal to 1, so that I can have that k is ln 0.955 divided by negative 30, and when I work through that I get that k is 0.00153. Okay, I've just solved for my two parameters, and I then know that m of t is going to be 20 times e to the negative 0.00153 t. Alright, and it says to me, hence calculate the amount of substance remaining after a further 30 years. So further 30 years means at time t equals 60. Okay, so now we're looking for m of 60. That's going to be 20 times e to the negative 0.00153 times 60, and that gives me 18.24 grams. So therefore, after a further 30 years, the mass is 18.24 grams. Alright, the B part of the question says determine the rate of decay at this time. Now remember, rate always implies a derivative, so rate of decay implies the derivative. Alright, and we have, let's just get our equation. So m of t is 20. So m t is going to be 20 times e to the negative 0.00153 t. And I can see I have a chain rule over here. So using the chain rule, m dashed of t will be negative 0.00153 multiplied by 20 multiplied by e to the negative 0.00153 t, and that is equal to negative 0.0306 e to the negative 0.00153 t. Now we're wanting the rate of change at this time, so at t equals 60. So therefore m dashed at 60 is equal to negative 0.0306 e to the negative 0.00153 times 60, and that is negative 0.0279 grams per year. Now the important thing is that in our sentence we now interpret that negative. Alright, so therefore the mass is decreasing, that's the word we're looking for, at a rate of 0.0279 grams per year after 60 years.